So here we're going to talk a little bit about circular motion and banked curves specifically. So when I say a banked curve, it's a very clear example of a highway curve or even a raceway curve, a curve on the road in which if you looked on it from the driver's perspective, you could see that the car is, or the highway itself is actually on an angle. And we would have talked about in class by this point the fact that it's on an angle because of the inertial effects of your circular motion. Really, you'd want to go, at any time you want to fly tangent to your curving motion, and you would actually cut off on a straight line if it were not for the, in this case on a banked curve, the gravity, the components of gravity that's pulling you towards the center. One thing to think about with a banked curve is that the free body diagram changes. And it changes because we really want to think about things in terms of centripetal force, which is directly towards the center of the circle. It's not down the incline. Maybe another thing I did want to say is that this is all in the absence of friction, and you might notice I wrote that up in the top corner here. So Fn is on a banked curve is mg by cos theta in absence of friction, which is all the typical examples that we do or test questions you might have in the grade 12 course. Having said that, I did put the last example, number 9, on your handout sheet, is a bonus, and it does incorporate friction. It's a bit beyond the scope of the course, but I would love to see you try to develop the formulas and come up with a maximum speed in the case of friction, if there's friction. Anyway, back to this. What we want to do right now is develop not just the formula for Fn, because it is something I want you to show me, but also the formula for centripetal force. So in this case, I've got my banked curve, and you're picturing, what you should picture here is my red dot, my car, or probably a car, is traveling into the board or into the page. And there's this slope that it's on. And one thing, before we even get into the math of it, I want to compare in your mind a banked curve versus an inclined plane, because they look the same. But because of the motion, the circular motion, it is very, very different. And if you just forget about math and forget about all that, just think about how you would feel. We talked about on the normal course on an inclined plane, that you can kind of picture that, there's less pressure between, say it's you sitting on an inclined plane, less pressure between you and that inclined plane than it would be if you're on a flat surface. And that's why it makes sense that on an inclined plane, Fn is mg times the cos of an angle. Remember that cos theta is always less than 1. Okay? It can't be greater than 1. So that means that your normal force on an inclined plane is always going to end up being less than the gravity. And I think that's fairly instinctive. There's less pressure between you and the surface when you're sliding down the surface rather than on a flat. Now, in this case, I'm telling you in advance that it's actually the total opposite. On a banked curve, the normal force, pressure between you and the surface, or the car, I guess, and the surface, is greater than gravity. And I say that because if you divide gravity, mg, your weight, or the weight of the vehicle, by something less than 1, you end up with a number greater than 1. And again, if you just put yourself in the position without any math, or just thinking about the experience of, and how, what you picture it would feel like if you're speeding around, imagine you're on a racetrack that's on an inclined plane. You can almost just feel yourself being sucked into the ground if you think about it enough. And that's all we're going to show is the math behind that. Okay, so going back to our what's going to become a free body diagram. The first, most sort of fundamental difference between how we treat an inclined plane and a banked curve is our coordinate system. Because like I said, we care about the center seeking. Well, center is this way. That's the center. That means that my coordinate system is this, where this is my x and this is my y. I'm back to straight up and down, not on an angle anymore. And that really does change the whole way you perceive an inclined plane problem or a banked curve problem. having said that, and I want to be able to find Fn using this as my reference system, okay? If I start drawing in, I still have gravity down, and I've got normal up here, and now if I want to take my normal force and draw the x and y components of normal. So my x and y components of normal, here's my x component of normal, and here's my y component of normal. And again, we're looking at the absence of any friction or anything like that. So this is really all that's going on in my problem. Just to get an idea of where the angles are. So this angle right here would be equal to theta. If you look at a z from here up. Okay. And if that's true, and this is 90 degrees between the normal and the plane, this up here must be theta. And I'm going to leave you to work that through yourself to make sure that makes sense to you. Okay. So, again, in the absence of anything else, and I think I might just go to another page just so I have it finished. So here's my object, here's normal. I'm going to draw a triangle here. Theta, here's F and X. And remember, the only other force that exists is gravity. These Fnx and Fny aren't actual forces, they're components of my normal, so they're not separate items. People are putting checks, I'm not drawing it quite. I don't want you to get confused and think that I'm making up 2 extra forces here. So those are just my components of normal. They're not actually forces of themselves. Now, if I was going to do a force balance in the up and down direction, or y direction, keeping in mind that this is my coordinate system, I can then say, because again, it's not moving up or down, this vehicle, the only way it's moving or accelerating in any direction is into the page. Z direction, whole different story. So in the up or down direction, I can say then that my F and Y equals Ft. Only force is X. And F and Y, you will notice, is adjacent to my angle. So then F N cos theta mg, or F N mg over. So this is an equation you will use related to banked curves, and that's why the normal force works out that way. The second thing that before we stop with this is maybe to come up with the main formula that you use is actually related to centripetal force. Now, we said that this is the direction towards the center. Well, there's only one force acting in that direction, and that's the horizontal, or the x component of Fn. Therefore, Fc, my center-seeking force, must be Fnx. That being true, whatever you call Fc, I'm going to call it mv squared over r, but there are other forms of it, is equal to Fn in the x direction would be Fn this time sine theta, because it is opposite my angle. If you look back to the triangle, Fn is opposite the angle, so it's sine. And then just to go just another step, for m squared over r equals, instead of writing Fn, why don't I write mg by cos theta? That's all times sine theta. And you might remember from math class that sine theta over cos theta tan theta. Therefore, mv squared over r equals m G times theta. Cancel the m's. And you end up with really the equation you most frequently use related to banked curves. Remember that a level 4 response on your test would include some development of that formula. So there often is a question related to banked curves, and obviously you can just use the formula. And that would be like a level 3 response. It's considerable knowledge. But to demonstrate an exceptional, or I can't remember what the right wording for level 4, but to demonstrate full understanding, I want you to show me that development as well. So I'll leave that to you if you want to put on your formula sheet. If you understand it and remember it, wonderful. Regardless, this is the formula to use, okay? And that's the banked curve formula.